Hello everyone and welcome to today's presentation on reversing a linked list. In this session, we will discuss the algorithm, its implementation, and how it works. Let's dive right into the topic. Our task is to reverse a singly linked list and return the reversed head. The input is a singly linked list where each node points to the next, and the output will be the same list with the nodes in reverse order. Let's look at a few examples. Given the input 1, 2, 3, 4 and null, the expected output would be 4, 3, 2, 1, null. This problem is essential because linked lists are commonly used in various algorithms and knowing how to reverse them can help solve many complex problems. Before we proceed, let's review the key concepts. A linked list is a data structure in which each node contains data and a reference to the next node. Reversing a linked list means altering the next references of the nodes so that the last node becomes the first and the first becomes the last. To reverse the linked list, we use an iterative approach. We maintain three pointers: prev, which initially points to null and will eventually point to the previous node as we reverse the list; car, which points to the current node we are processing; next node, which temporarily stores the next node to avoid losing the list reference during the reversal process. By iterating through the list, we adjust the next pointer of each node to point to the previous one, effectively reversing the direction of the list. Let's break down the algorithm steps. First, we initialize three pointers: prev equals to null, car equals to head, and next node assigned null. Then we iterate through the list. In each iteration, we store the next node assigned current node, current.next. Reverse the current node's pointer and move previous and current one step forward to continue the process. Once we reach the end of the list, prev will be the new head of the reversed list. Here is the code implementation of the solution in C++. This is a simple iterative implementation. We traverse the list once, updating the pointers to reverse the list. Now let's discuss the time complexity. Since we only traverse the list once, the time complexity is big of n, where n is the number of nodes in the list. For space complexity, we only use a constant amount of space for the three pointers, so the space complexity is big of 1. This is an efficient solution. There are a couple of important edge cases to consider. Empty list. If the input is null, the output will also be null. Single node list. If there is only one element, reversing the list will result in the same list as there's nothing to change. In conclusion, we have successfully reversed a singly linked list using an iterative approach. This solution runs in linear time and uses constant space, making it both efficient and straightforward. That's all for today's presentation. Thank you for your attention. Welcome to the presentation on the problem minimum cost to make at least one valid path in a grid. In this presentation, we will walk through the problem statement, approach, solution, and its time complexity. Let's start with the problem overview. We are given a grid and each cell contains an arrow pointing in one of four possible directions. Our goal is to find the minimum cost to create a valid path from the top left to the bottom right of the grid. Modifying a sign in the grid has a cost of 1, and we can modify each sign at most once. The challenge is to figure out how to do this with minimum cost. Here's an example to illustrate the problem. Consider this grid 1111, 2222, 1111, 2222. The output is 3, which means we need to modify 3 signs to create a valid path from the top left to the bottom right with a cost of 3. The grid's arrows are mapped to specific directions. Arrow 1 indicates moving right, 2 moves left, and 3 moves down, 4 moves up. Each direction defines how we move from one cell to another, and we will use this information to decide which signs need modification. The goal is to find the minimum cost to create at least one valid path. We use a modified breadth first search or BFS with a DQ. The DQ ensures that we first process cells with zero cost moves, followed by cells where modifications are needed. This allows us to efficiently minimize the cost of changes. Now let's break down the steps. First, we perform BFS with a DQ. We initialize a 2D array to track the cost to reach each cell. For each cell, we check all 4 possible directions. If the current direction does not match the grid's arrow, we add a cost of 1. The DQ helps us manage these moves efficiently. Here's a quick look at the data structures used in the solution. We have a cost array to track the minimum cost for each cell, a DQ to process cells, and a directions array to handle the 4 possible movements. The DQ helps us prioritize moves with zero cost. In the first part of the code, we initialize the grid's dimensions and the directions array. We also set up a 2D array to store the minimum cost for each cell. The DQ is initialized with the top left cell, and we start with a cost of 0 for that cell. Now let's look at the BFS loop. We process the front of the DQ and check for all 4 possible directions. If we move to the neighboring cell, we calculate the new cost. If the direction does not match the arrow in the grid, we add a cost of 1. We then update the DQ based on whether we add a cost or not. Finally, we return the minimum cost to reach the bottom right cell after processing all the cells. The DQ ensures that we process the cells in the most optimal order, with zero cost moves processed first. Let's analyze the time and space complexity. The time complexity is big of m times n, where m and n are the dimensions of the grid. Each cell is processed once, and for each cell we check up to 4 neighbors. The space complexity is also big of m times n due to the cost array and DQ storage. In conclusion, we have solved the problem using BFS with a DQ, ensuring that we process moves optimally. Modifications are tracked to minimize the cost of changing signs, and the minimum cost is efficiently calculated. This approach provides an optimal solution to the problem.